Ever just stop and think how weird it is that, a load of non-living stuff, just chemicals, somehow managed to get together and, well, become alive?
It is pretty mind-boggling when you phrase it like that.
Like, how does that even happen? It feels almost impossible. Socks organizing themselves, but like way, way bigger.
Right. And that's exactly what we're diving into today, the origin of life.
Yeah.
We're looking at some ideas around this concept of the fitness of the cosmos for life.
Trying to pull out the really interesting bits without, needing a PhD in biochemistry to follow along.
Exactly. Because it's a huge question, drawing on everything from chemistry to, well, cosmology.
And the thing is, even with all our science, we still don't really know how life kicked off, do we?
That's one of the most humbling parts. The source material we're looking at is pretty clear on this. We have ideas, some strong intuitions, maybe
Guesses?
educated guesses, yeah,
Yep.
but not really solid, testable hypotheses for that very first spark.
Right. We can describe life now, this amazing, like, self-contained network of reactions all happening in water that can copy itself and change.
Adapt, yeah.
But how that started, it feels like. Well, the source puts it brilliantly. How could a chemical sludge spontaneously become a rose, even with billions of years to try?
That really captures the scale of the challenge, doesn't it? The sheer improbability, you might say,
Yet here we are, talking about it.
which tells you something happened. And amidst the mystery, some things seem, well, fundamental.
Like water.
Ah, yes,
Yeah.
water. Always water.
According to our source, it's the essential medium. All life we know depends on it. No exceptions found so far.
Okay, so water's the stage. What about the play itself? It's complex, right? Insanely
Really?
complex.
Oh, absolutely. You've got this intricate dance of chemical reactions inside every single cell. And that dance relies heavily on catalysts.
Enzymes.
Enzymes, yes. These molecules are crucial. They speed up reactions, guide them, basically make the whole intricate network possible.
So they're like the conductors of this microscopic orchestra. That's a great analogy. They allow all these different chemical components to act like a single coherent entity. It's not just chaos.
This communication.
Definitely. The source calls it intricate conversations. Molecules influencing the enzymes that make them, responding to signals from inside and outside the cell. It's remarkably sophisticated.
Okay, so where did the first bits come from? The basic ingredients for this cellular soup.
Well, the source mentions a few possibilities. Things like hydrothermal vents deep in the ocean, maybe lightning strikes, impacts from space, even solar radiation.
So energetic events creating some basic chemical building blocks.
Potentially, yes.
Yeah.
Plausible ways to get some of the raw materials. But, and this is the key thing, how do you get from those basic parts to the incredibly responsive, robust network of a living cell?
That's the big leap.
That's the core mystery, yeah.
All right, let's zoom out a bit. This idea of the fitness of the environment. What's that about? It sounds like the universe itself might be set up for life.
That's the core idea, that the fundamental laws and properties of the cosmos aren't just random, but might actually be conducive, maybe even biased towards life emerging.
And this isn't a new thought.
Not at all. The source points way back to L.J. Henderson. His book, The Fitness of the Environment, came out in 1913.
Wow. Okay, so over a century ago.
He was arguing that things like the properties of water, of carbon, they seem uniquely suited for the kind of complex chemistry life needs.
The source mentions he was a bit of a complex character himself, distrustful of intellectuals or something.
Yeah, there's a little biographical note about that from John Edsall. Interesting detail, but the main takeaway is Henderson's scientific point about this environmental fitness.
Even if he used some maybe slightly philosophical language sometime.
Right. The source notes he used terms we might see as metaphysical or teleological, but he still considered fitness a scientifically valuable concept.
Okay, so fitness. And you mentioned carbon. Carbon's the star player here, isn't it?
Absolutely central. Henderson highlighted carbon, hydrogen, and oxygen. Carbon's special because of its electron structure.
It can bond with lots of stuff.
Exactly. It's in the middle, so it can share electrons easily, forming single, double, triple bonds, linking up into long chains and complex rings. It's the backbone of organic chemistry.
Mhm.
Methane, ethane, all those molecules the source mentions show this versatility.
So the building blocks themselves have these like built-in properties perfect for complexity,
Mm,
which kind of leads to fine-tuning, right?
precisely. The idea that the universe's fundamental constants, gravity, the electromagnetic force, things like that, seem to be set within a very narrow range. If they were much different, life as we know it just couldn't exist.
And it's not just physics. The source says this applies to biochemistry too.
Yes, the book apparently extends this idea, looking for sensitive, finely tuned features within biology and astrobiology as well. But it also adds a note of caution, particularly for theology,
How so?
suggesting that focusing only on design or fine tuning as, like proof of divine action, can be problematic. It might raise other difficult questions, maybe about suffering or imperfection.
Hmm. Okay, so it's complex. And there's this idea of explanatory pluralism, different levels of explanation.
Exactly. Like the analogy in the source, explaining why you're cooking hot dogs by saying, I want hot dogs, is a different kind of explanation than analyzing the chemistry of the burning logs.
One's about intention, the other's about physical process.
Right. And theological explanations might operate on that intentional or purposeful level, distinct from the physical cause and effect level science usually deals with. The source mentions Conway Morris being aware of this boundary.
Okay, that makes sense. So the source then talks about chance and necessity, saying they're too simple.
Yeah, it argues they're lifeless abstractions, that nature is more like a story
A story. How?
that unfolds over time, blending contingency, the unpredictable, chance events with necessity, which is the consistent, lawful framework everything operates within.
So unexpected things happen, but they follow certain rules.
Exactly. Chance provides the openness, the possibilities, while necessity provides the reliable structure. You need both for the kind of unfolding narrative we see in nature, including evolution.
I like that. It feels more dynamic. Okay, complexity again. Irreducible versus staggering.
Right. Staggering complexity. Yeah. This is Dennett's idea. The source points to the sheer number of possibilities. Think of all the ways letters could be combined versus the tiny fraction that make a readable book.
All the possible DNA sequences versus the ones that actually work.
Precisely. The number of functional combinations is minuscule compared to the total possibilities. This staggering complexity can look like it must have been designed.
But it could arise through selection.
That's the counterargument. You can map pathways where selection gradually builds up that complexity, even if the end result seems astronomically improbable at first glance.
Got it. Which ties into contingency and evolution, like Stephen Jay Gould's idea. If you rewound the tape.
Rewound the tape of life and played it again, yeah. Gould argued it's highly unlikely you'd end up with humans, or anything much like us. He emphasized the role of unpredictable chance events.
But Dennett disagrees, or at least nuances it.
Dennett's point, as presented in the source, is more about the level of description. Maybe not Homo sapiens exactly, but could intelligence, tool use, complex societies arise again through a different path? He suggests maybe so. The source adds that Gould's work doesn't definitively rule that out.
So the jury's still out on whether intelligent life is a total fluke or maybe a more probable outcome of complex evolution.
It's a huge debate. And the source makes a crucial point. Often these debates are shaped by underlying assumptions we don't even realize we have. Metaphysical presuppositions.
Our basic beliefs about reality influencing how we interpret the science.
Yes. It even notes that Darwin's own changing views on God weren't just about evolution, but also tied to his doubts about whether the human mind could even grasp ultimate truths.
Fascinating. Okay. Briefly then, fine-tuning in cosmology. Any examples?
The source mentions Dirac and his large number hypothesis, noticing weird coincidences between big numbers in physics and wondering if it meant something deeper. An early precursor, really.
And more recently.
Things like cosmic inflation theory, which addresses some fine-tuning problems, and of course, the multiverse idea.
Ah, the multiverse. The idea that there are countless universes and we just happen to be in one where the constants are right for us.
That's one type of anthropic explanation, yes. Though, as the source points out, it doesn't explain where the multiverse itself came from.
Right. Pushes the question back. Okay, final stretch. Biogenesis, the actual start. How life got going from non-life.
Yeah, the really hard problem. The source mentions hypotheses about early life starting in hot, deep places, like near hydrothermal vents.
But heat's a problem too, right? For molecules like DNA.
It is. There's a temperature bottleneck. Above about 100 degrees Celsius, proteins in DNA start to break down, which makes things tricky for life starting in really hot environments. Another delicate balance needed.
And then there's convergence. What's that?
Convergence is when unrelated species independently evolve similar features because they live in similar environments or face similar challenges.
Like cacti and those African plants that look like cacti but aren't related.
Exactly. Succulent, spiny, water-storing adaptations popping up independently in deserts on different continents. The source says this happens at the biochemical level, too.
Even with molecules.
Yes. Different proteins can evolve to fold into very similar 3D shapes to perform similar functions. It's seen as further evidence for evolution, finding effective solutions repeatedly.
Which hints that maybe some outcomes are more likely than pure chance would suggest.
That's the implication the source explores, that this fitness of the environment might steer evolution towards certain kinds of complexity. It even mentions the idea of an evolutionary inevitability of mind.
Whoa, okay. That's a big thought.
It is. The idea that convergence isn't just about body shapes, but might push towards intelligence eventually.
So wrapping this all up, the origin of life is still a massive mystery.
Absolutely. Profoundly mysterious. But looking at it through this lens of cosmic fitness, chemistry, evolution, it reveals a universe that seems strangely permissive, maybe even encouraging of complexity.
Even if we don't know the exact steps from chemical sludge to, well, us.
Right. The underlying rules, the properties of matter, the way evolution works through contingency and necessity they seem to allow for, and perhaps even favor, the emergence of complex adaptive systems.
Which leaves us with a pretty wild final thought, building on that convergence idea. If life does pop up somewhere else out there, will it also eventually lead to something that asks these same questions? Something that tries to figure out its own beginnings, just like us, and what would their story sound like?
That is definitely something to ponder. A cosmic cliffhanger indeed.